will do this in the kinetics part very extensively. So going back to C1 equilibrium and reacting species, right? So you select the equivalence ratio and you then click on this plus minus here. See this? And now you select the equivalence ratio range that you want, right? So let's say we want to start at 0.6. And we want to end at 1.4. And the number of values, 0.6, 0.7, 0.8, 0.9, let's say 10 values. So we can have a nice graph, populate. So you see now that we're calculating 0.6, 0.68, 0.78. Okay, so we're going to calculate all these. Done, right? So now we go to run calculations, display detail. So now we're going to select all of these. And we're going to run all of them. Where does it say run selected? This here? Yeah. So now it's going to take a little bit more time, but it's going to do the entire thing. And so now we're going to be able to construct the graph. So here, instead of going to the output file, we go to the plotting software. Next step. And so now we're interested just in the equivalence ratio and the temperature. Although we're going to get a lot of other stuff that we're going to analyze, all the concentrations as a function of time and all that. So we'll take a look at that later on. But now, let's see, what do we have here? Process solution data, right? You click on process solution data. So now it's processing all the output files, the 10 output files. And once that is done, there will be a new window that appears where you can now select your independent variable and your dependent variable. So let's see if I can remember how this works. So now you select the equivalence ratio and the temperature, right? Equilibrium temperature. Create plot, right? So something is wrong with this plot, right? It shouldn't look like this, right? This number, so it should look like this, right? So this would be 0.6, 0.7, 0.8, 0.9, 0.951. So this should be 1.5, 1.05. So you can construct the graph using the post-processing software that Ken knows. Something is wrong here, but you see that we can select the equivalence ratio as the independent variable. The old-fashioned way, of course, is more secure at this point because I need to show you some of the details and I need to remind myself of some of the details how to construct this graph. This point obviously should be neglected because and we need to change the scale here on the x-axis. It should be the equivalence ratio, right? So we're heading in that direction even without reading the manual, and I will show you how to do this in more sessions that we will have both here in the lab and I'll show you that in class as well. So this is for methane. Let's do now one more case. Let's close all this. And go back to what other fuel do we need? Can you look at the statement of the problem?
CH2H6, I guess.
Not CO2. What other fuel?
C2H6.
C2H6.
Ethane, right? So let's go to C1 equilibrium. A reactant species. Let's see what we have. We want to or maybe we can still use the equivalence ratio as a parameter. So let's eliminate methane. And let's select C2H6, right? Ethane, C2H6, 1 mole of ethane. Let's add that. And the oxidizer mixture, of course, is going to be the same. So now go to run calculations, display detail. And so you see in this case again, we are using the equivalence ratio as our independent variable. And in the previous example, we selected 1.0. We shouldn't select 1.0. We should start at 0.6. So we'll start at 0.6, 0.68, 0.77, right? So let's select this one, this one, this one, this one, this one, this one, that one, and so on and so forth, right? So we have selected a bunch of equivalence ratios from 0.6 to 1.4, and we want to solve at each equivalence ratio for the flame temperature. So we want to run selected cases. So let's do that. So this takes a little bit longer, as you see. Next step. So you see that it is post-processing. And when it's finished, a new screen will come up. So we want the x variable to be our equivalence ratio. So the x variable is equivalence ratio. You see it anywhere? There it is, equivalence ratio, right? So and our y variable is equilibrium temperature. Create y. There it is. So again, we have something wrong, right? So this point now is again off. Something is wrong there, but the general trend is correct. So at 0.6 it's 1700, it peaks at 1.05, right? And it is skewed to the fuel-rich region, right? So at 1.4 the flame temperature is much higher than at 0.6. So this small problem that I haven't figured out what the problem is, you can ignore it. Okay? So in the next 10 minutes that we have, I will walk around and make sure that you can do this.